Welcome to Section 1.2, Precalculus Review 2. We will review rational expressions, inequalities, and absolute value, three algebraic tools that appear repeatedly in calculus. A rational expression is a quotient of polynomials. Domain restrictions come from the original expression and do not disappear when a factor cancels. Cancellation simplifies the formula, not its personal history. Factor both polynomials first. The common factor x plus 3 cancels, but x equals -3 remains excluded because it made the original denominator 0. The numerator contains a common factor of 2 times x squared plus 1. Factoring it reveals the cancellation and leaves a much simpler expression. When an expression looks intimidating, it may simply be wearing too many parentheses. For multiplication, factor before multiplying. For division, first replace division by multiplication by the reciprocal. This is one of the rare moments when flipping something actually improves the situation. Factoring reveals two common factors that cancel. The final expression is simpler, but all three restrictions come from the original denominators. After multiplying by the reciprocal, common factors cancel. We must also exclude 0 because the original divisor becomes 0 there. Division by 0 remains mathematics' least negotiable red line. An addition sign blocks cancellation. Always factor before canceling so the multiplicative structure is visible. Addition signs are tiny algebraic security guards against cancellation, and they take the job seriously. Fractions can be added or subtracted only after they share a denominator. The LCD gives them common ground, which is more diplomacy than most fractions deserve. The first expression already has a common denominator, but parentheses are essential when subtracting the second numerator. The second expression requires an LCD before the numerators can be combined. Factoring the quadratic denominator shows that the first fraction already contains the full LCD. Only the second fraction needs an extra factor of x minus 3. After using the LCD, distribute both multipliers carefully. The constant terms cancel completely, leaving only x in the numerator. Sometimes algebra cleans its own room, though we should not expect this behavior consistently. A complex fraction is simply a fraction containing smaller fractions. Choose the method that produces the cleaner calculation. It is a fraction within a fraction, because apparently one level of bureaucracy was not enough. Combine the fractions in the large numerator and denominator separately. Dividing the results causes the common factor xy to cancel. Multiplying every small term by x clears all the smaller denominators at once. This method is efficient, provided x is distributed to every term and no fraction is left behind. Simplify the large numerator and denominator, then multiply by the reciprocal. The cancelled factor x plus 2 still contributes the restriction x not equal to negative 2. Restrictions never accept a cancellation as an alibi. Rewrite each negative exponent as a reciprocal, combine the smaller fractions, and factor the difference of squares. 4 restrictions are required because both the small denominators and the large denominator must remain non-zero. Rewrite the radical term using the common denominator square root of 2x squared plus 3. Because the quantity under the radical is always positive, every real x is allowed. Conjugates differ only in the sign between their terms. Their product is a difference of squares, so the radical cross terms disappear. They are mathematical opposites who cooperate surprisingly well. The conjugate changes the denominator into 9 minus 5. Since that equals 4, it cancels the factor 4 in the numerator and leaves 3 minus square root of 5. Multiplying by the conjugate turns the numerator into x, which cancels with the denominator. This maneuver will later be useful in difference quotients, where radicals often pretend to be obstacles. The conjugate must include both terms of the binomial. Multiplying only by the radical creates more radical terms instead of eliminating them, which is algebra's version of putting out a fire with confetti. Adding or subtracting preserves the direction of an inequality. Multiplying or dividing by a negative number reverses it because the order of numbers is reflected across 0. Dividing by negative 3 reverses the inequality, so x is greater than or equal to negative 4. The filled endpoint shows that negative 4 is included. Multiply by 3, distribute on the right, and isolate x. No reversal occurs because we never divide by a negative number. Perform each operation on all 3 parts of the compound inequality. Dividing by negative 7 reverses both inequality signs. Then we rewrite the answer from smaller to larger. Critical numbers are zeros and undefined values. They divide the number line into intervals on which the sign cannot change, so one test number determines the sign of an entire interval. Factoring produces critical numbers negative 3 and 2. Testing one point in each interval shows that the quadratic is negative between its zeros and positive outside them. Test numbers show that the rational expression is positive on the outer intervals. The 0 at -1 is excluded because the inequality is strict, and 3 is excluded because the denominator vanishes there. Cross multiplication is unsafe when the denominator's sign is unknown. A test number analysis handles the positive and negative cases automatically. Blind cross multiplication is less a shortcut and more an algebraic blunder. The critical numbers are negative and positive square root of 5. The test values show that x squared minus 5 is positive outside those zeros and negative between them. The factors give critical numbers -5, 0, and 5. Test numbers show alternating signs. Absolute value represents distance from the origin, so it is never negative. For instance, both 5 and -5 are at a distance of 5 units from the origin. Absolute value returns the non-negative distance from 0. In Part C, 2 minus square root of 7 is negative, so its opposite is square root of 7 minus 2. Absolute value removes negativity, not responsibility for checking the sign. An absolute value less than a positive number describes points inside a distance from the center. Greater than describes points outside. The words inside and outside are often easier to remember than 4 separate formulas. This expression asks for all values within 5 units of 2. Greater than produces 2 outside regions, so we solve 2 separate inequalities joined by or. Absolute value does not distribute across addition. The correct relationship is an inequality, not an equation. That completes section 1.2. Focus on the structure of each expression rather than memorizing disconnected tricks. A shortcut that loses a restriction is merely a scenic route to the wrong answer.